Hello and welcome to the Deep Space Relax channel. I'm truly glad you're here. Maybe it's been a long day, or maybe you simply enjoy drifting off while thinking about stars, galaxies, and the quiet mysteries of the cosmos. Either way, tonight's journey is meant for you. There's nothing you need to do right now. Just allow your body to relax, your mind to slow, and your thoughts to wander. Because tonight, we're exploring the universe itself. Not just a single galaxy or star, but the vast, expanding whole. We'll move gently from one idea to the next, learning about black holes, ancient light, dark matter, and distant galaxies. Some things may surprise you. Others may linger, like a soft thought at the edge of sleep. And if these calm explorations help you rest, feel free to like and subscribe. It helps others find their way here as well. Now, if you're ready, let's begin. The universe might be older than we think. Most modern estimates place its age at about 13.8 billion years. This number comes from measurements of the cosmic microwave background and calculations of how quickly the universe is expanding. But not every method agrees. Some observations of very ancient stars and galaxies suggest they could be older than that estimate allows. Others question the assumed rate of expansion or propose that dark energy may evolve over time. These tensions remain unresolved, and most astronomers still accept the 13.8 billion year figure. But the questions persist. Could the universe be older? Did we overlook something fundamental? It's possible that what we consider the beginning was only one chapter in a longer, stranger story. There are thousands of rogue planets drifting through space without stars. Not every planet orbits a sun. Some are completely unbound, traveling alone through the galaxy without a star to warm them or illuminate their skies. These rogue worlds may have formed normally and later been ejected from their systems through gravitational chaos. Others might have formed independently, like failed stars. They are dark, cold, and nearly invisible unless they pass in front of distant background stars or glow faintly in infrared light. Astronomers estimate there may be billions of them in the Milky Way, possibly even more than the number of stars themselves. Each one is a silent world, drifting in darkness, spinning alone in the immense spaces between. No sunrises, no sunsets, just endless night broken only by distant starlight. The universe may recycle itself through infinite cycles. The standard cosmological model describes a universe that began with the Big Bang and may continue expanding forever. But some theories imagine a different possibility, a universe that moves through repeated phases of expansion and collapse. In these models, the universe doesn't end in a cold fade or a final crunch. Instead, it resets. After reaching a certain state, it might contract inward, then rebound into a new expansion. Each cycle could erase previous structures while preserving subtle traces of what came before. These ideas remain speculative, but they are compelling. They suggest that the universe may have no absolute beginning or end, only a rhythm stretched across unimaginable spans of time. One universe giving rise to another, again and again. The oldest light we can observe comes from about 380,000 years after the Big Bang. Before that moment, the universe was a glowing fog, so hot and dense that light could not travel freely without scattering. But as the universe expanded and cooled, it reached a turning point. Atoms formed, the fog cleared, and light became free to move. That ancient radiation is the cosmic microwave background, and we can still detect it today. It is the oldest direct signal in existence, not from stars or galaxies, but from the universe itself as it first became transparent. The photons we see now have been traveling for more than 13 billion years, stretched by cosmic expansion into long, cool microwaves. This light is faint, yet ever-present, a quiet glow that carries the memory of the universe's earliest clarity. Some stars may host planets made almost entirely of diamond. In certain planetary systems, the chemistry differs greatly from our own. If a planet forms in an environment richer in carbon than oxygen and the pressures grow high enough, something extraordinary can occur, a diamond world. Astronomers have identified at least one such candidate, a dense planet orbiting a pulsar, likely the remnant of a dead star. Based on its mass, density, and composition, the entire world may consist largely of crystalline carbon, essentially a giant diamond. It's far too hot to sparkle, and it wouldn't resemble a gemstone up close. But deep beneath its surface, immense carbon lattices could extend for thousands of kilometers. These unusual worlds are rare, yet they remind us how diverse the universe can be. A planet of rock, a planet of gas, and sometimes a planet of crystal. The universe may have no edge, only endless curvature. It's natural to imagine space having a boundary, a limit we could reach if we traveled far enough. But space does not appear to work that way. According to general relativity, the geometry of space depends on its contents. Current evidence suggests that the universe may be either infinite or so vast and curved that it loops back on itself. If that's true, one could theoretically travel in a straight line forever and eventually return to the starting point, not by hitting a wall, but by following the curvature of space. Much like traveling around Earth reveals no edge, only a globe, the universe may function in a similar way on a far grander scale. Not infinite in space perhaps, but infinite in journey. The sun may once have had a twin, and it could still exist somewhere. Some astronomers propose that our sun was born with a companion star formed from the same cloud of gas and dust over 4 billion years ago. Many stars form in pairs, and there is no clear reason our sun would have been different. If this stellar sibling existed, it likely drifted away long ago, separated by the slow gravitational pull of the Milky Way. It might still be out there, orbiting the galaxy along a different path, unseen by us today. Some theories even link this hypothetical twin, nicknamed Nemesis, to extinction patterns on Earth, though there is no solid evidence supporting that idea. Still, the thought remains that our steady sun, alone in our sky, may once have shared its birth with a silent companion now lost among the stars. A single drop of neutron star material would weigh more than Mount Everest. Neutron stars are the collapsed cores of massive stars, incredibly dense remnants left behind after supernova explosions. They measure only about 20 kilometers across, yet their mass exceeds that of our sun. Inside them, matter is packed so tightly that a single teaspoon would weigh billions of tons. If you could imagine just one raindrop of neutron star substance, it would outweigh any mountain on Earth. That level of density defies everyday experience. Atoms are compressed so intensely that electrons and protons merge into neutrons, creating what is essentially a superfluid sea of neutrons. Neutron stars are extreme objects, small, dark, immensely heavy, and often spinning at extraordinary speeds. Yet within their compact mass lies the memory of stellar collapse, a final state where matter becomes almost pure gravity. Light from one galaxy can reach us from multiple directions. Light does not always travel in straight lines. In regions where gravity is exceptionally strong, near massive galaxy clusters, for example, space-time itself bends. This curvature deflects light, much like glass bends a beam. The phenomenon is known as gravitational lensing. One of its strangest effects is that we can sometimes observe multiple images of the same distant galaxy from different angles. These appearances may look like arcs, smears, or even complete rings. They are not duplicates in space, but multiple paths that light has taken through warped space-time before arriving at our eyes. In rare cases, astronomers have even witnessed the same supernova appear to explode more than once as its light traveled along different gravitational routes. It's a quiet reminder that in the universe, even light can wander, take the long way around, and still eventually find its destination. The first stars may have shone 1,000,000 times brighter than the sun. The earliest stars were unlike any we see today, formed from pure hydrogen and helium left after the Big Bang. These so-called population 3 stars likely contained no heavier elements. Without metals to cool them, they grew enormous, hot, and short-lived. Some may have been hundreds of times more massive than our sun. They would have burned through their fuel rapidly, shining perhaps 1,000,000 times brighter before collapsing in spectacular explosions after only a few million years. None of these primordial stars survive today, but their brief existence transformed the universe. They forged the first heavy elements, seeded galaxies with enriched material, and prepared the stage for everything that followed, including us. Their light has long faded, but their signatures remain in the chemistry of ancient gas clouds and in the subtle structure of the early cosmos. Dark matter flows through your body as you sleep. As you rest, dark matter moves silently around and through you. It isn't an invisible fog, but a form of matter that does not interact with light. It neither reflects, emits, nor absorbs it. Yet it has mass and responds to gravity. Our galaxy is embedded within a vast halo of dark matter. As Earth travels through this halo, trillions of dark matter particles are believed to pass through every square centimeter of your body each second. They do not collide with your atoms. They leave no trace. But they are there, ghost-like, constant, essential. Without dark matter, galaxies would not remain bound together, large-scale cosmic structures would not form, and the universe would look entirely different. We still do not know what dark matter is made of, but we do know this. It is part of your environment, streaming through you continuously and silently, even as you sleep. Some galaxies shine despite containing almost no stars. In the far reaches of space, astronomers have identified galaxies that glow faintly while hosting very few stars. These ghostly systems contain gas and dark matter, yet show little evidence of ongoing star formation. Some may have lost their stars through violent gravitational interactions. Others may never have formed many stars at all. A few are nearly invisible, except in specific wavelengths. Faint smudges revealed only in deep sky surveys. These galaxies challenge our understanding of how galaxies form and evolve. If they contain abundant dark matter, why did they fail to build stars? If they once had stars, where did they go? These dim and quiet systems drift through space like forgotten remnants of cosmic history, reminding us that not every galaxy blazes with light. Some simply float, unanswered and unseen. The universe contains a cold spot that should not exist. Within the cosmic microwave background, the faint radiation left from the Big Bang, astronomers have found a region of sky that is unusually cold. It is not merely slightly cooler than its surroundings. It is significantly colder and far larger than expected. This cold spot spans hundreds of millions of light years, and its characteristics do not perfectly align with the smooth randomness predicted by early universe models. Some scientists suggest it may be the imprint of a massive cosmic void. Others speculate about even stranger possibilities, such as a collision between our universe and another during the earliest moments of cosmic inflation. No existing explanation completely accounts for it. The cold spot remains one of the most quietly disturbing mysteries in cosmology. Not a loud anomaly, but a subtle hint that something about our universe might not be as it appears. The moon is gradually drifting away from us. Each year, it moves a tiny bit farther from Earth, roughly 3.5 centimeters. That's about the same speed your fingernails grow. This gradual retreat has been underway since the moon formed around 4.5 billion years ago. At that time, it was much closer, and a day on Earth lasted only a few hours. The reason is tidal friction. As the moon tugs on Earth's oceans and the planet rotates beneath them, a small transfer of energy steadily nudges the moon outward in its orbit. It's a silent, persistent process, invisible on human timescales, yet undeniable across vast stretches of time. In the distant future, Earth and the moon could become tidally locked, forever showing the same face to one another. For now, it continues drifting away bit by bit as we spin beneath its distant glow. Binary stars are able to exchange their outer layers like partners in a dance. In certain binary systems, the two stars orbit so closely that their outer atmospheres begin to meet. As they evolve, one star may expand and pour material onto the other, forming a delicate spiral flow of matter. Sometimes this exchange remains calm and steady. At other times, it sparks bursts of light, rapid spinning, or even a total merger. The physics is intricate, yet the image feels strangely elegant. Two stars bound in orbit, turning close enough to touch and merge. One may be stripped down to a radiant core, while the other grows swollen and enriched. Their destinies are intertwined. Some of the universe's most unusual objects, such as certain supernovae or compact neutron star pairs, begin as these quiet, touching binaries. A reminder that in space, even stars can share, transform, and sometimes embrace. The vacuum of space is not truly empty. Even in the deepest, darkest regions of space, far from any star or galaxy, the universe is never completely void. According to quantum physics, what we call a vacuum is actually a field of activity. Tiny particle-antiparticle pairs flash into existence and disappear almost instantly. These quantum fluctuations occur constantly everywhere, forming a restless backdrop to reality itself. They can affect the movement of particles, influence fields, and even contribute to the energy of empty space. This plays a role in what we call dark energy, the mysterious force driving the universe's accelerating expansion. So when we imagine deep space as silent and motionless, that picture is only partly accurate. Beneath the stillness lies a dance of probabilities, a hidden murmur of appearance and disappearance. always just beneath the surface of nothingness. Time may pass at different speeds in different regions of the cosmos. We tend to think of time as constant, a steady rhythm flowing identically for everyone everywhere. Yet in reality, time is profoundly connected to gravity, motion, and the very curvature of space-time. In areas where gravity is intense, such as near a black hole or within a dense galaxy cluster, time moves more slowly compared to places where gravity is weaker. This is not merely theoretical. It has been verified by experiments, satellites, and atomic clocks. Still, some cosmologists question whether time might also vary on even grander scales. Could separate regions of the universe experience time at slightly different rates because of how the cosmos expanded in its earliest moments? The idea remains speculative, but it opens unusual possibilities. In a universe governed by relativity, even time may not be absolute. It can stretch, slow, or curve, subtly shaped by the space through which it moves. The Milky Way possesses a hidden halo far larger than the visible galaxy. When we observe images of the Milky Way, we see a luminous spiral of stars, dust, and gas arranged in graceful arms. But encircling this familiar form is something immense and largely unseen: the galactic halo. It is a vast sphere of thin gas and dark matter extending far beyond the galaxy's visible edge, reaching distances many times greater than the span of the disk itself. This halo contains ancient star clusters, wandering stars, and enormous quantities of unseen mass, bound together by gravity and shaped by a history of mergers and collisions. It quietly contributes to the galaxy's stability. Although we cannot observe it directly, we infer its presence from the motion of stars and the bending of light. The Milky Way, it turns out, is only the bright center of something much greater, a glowing core wrapped in invisible arms. We have detected light from a galaxy that existed just 200 million years after the Big Bang. The universe is roughly 13.8 billion years old. But light does not travel instantly. It moves through expanding space, stretched and slowed along its journey. That is why we see galaxies not as they are now, but as they were long ago. Recently, astronomers using the James Webb Space Telescope identified light from a galaxy that formed only 200 million years after the Big Bang, a brief moment on the cosmic timeline. That light has been traveling toward us for more than 13.5 billion years. The galaxy itself is small, faint, and primitive, yet it carries clues about how the first structures emerged. Observing it is like peering through a narrow window into a world we were never meant to witness. The universe in its earliest chapters, when darkness was only beginning to give way to stars. The large-scale structure of the universe resembles a neural network. When astronomers chart the positions of galaxies across immense distances, an unexpected pattern appears. Galaxies are not randomly dispersed. Instead, they gather along thread-like filaments with enormous empty regions, cosmic voids lying between them. This interconnected network stretches across billions of light years and is often referred to as the cosmic web. What feels uncanny is that when viewed on the larger scales, this structure strikingly resembles a neural network like the one inside the human brain. Dense clusters of galaxies resemble neurons, while the filaments look like axons linking them together. Naturally, the similarity is purely structural. The universe is not conscious. Still, it is quietly beautiful to reflect on how the largest known structure and the one inside your own mind, shaped by entirely different physics, can appear so remarkably alike. Stars can sing across the vacuum of space. There is no air in space, so we cannot hear sound as we do on Earth. Yet stars still produce sound, deep, slow vibrations that travel through their interior gases, much like seismic waves move through a planet. These pressure waves cause a star to pulse and oscillate, and scientists can detect them by measuring tiny variations in a star's brightness or surface motion. The scientific field devoted to this study is known as asteroseismology, literally the seismology of stars. Each star possesses its own internal frequencies, like a fingerprint determined by its size, structure, and age. By listening to these stellar vibrations, researchers can look inside stars and understand what is happening beneath their surfaces. It is a form of cosmic echolocation, a way to hear the music of stars across light years, even if their song remains silent to human ears. Some stars are older than the galaxies they inhabit. Galaxies are not assembled all at once. They develop over time, merging with smaller systems and drawing in stars and gas from surrounding regions. This means certain stars within a galaxy can be older than the galaxy's present structure. They may have formed in earlier, smaller galaxies that later combined into a larger one. These ancient stars often reside in the outskirts or within globular clusters, tightly bound groups orbiting far from the galactic center. Some are more than 13 billion years old, nearly as ancient as the universe itself. They preserve the chemical imprint of a younger cosmos, when heavy elements were scarce and only the simplest atoms existed. These stars are like fossils, quiet survivors from before the galaxy fully assembled. Their light is ancient. Their stories began long before much of what we know had taken shape. There are galaxies without dark matter, and we still don't understand why. Dark matter is believed to be the invisible substance that binds galaxies together. It explains why stars in the outer regions move faster than expected and why galaxies cluster the way they do. Yet in recent years, astronomers have identified galaxies that appear to challenge this idea. Galaxies that behave as though they contain no dark matter at all. Their stars move as if only visible matter exists. This finding was surprising and does not fit neatly within current models. Some researchers suggest the dark matter may have been stripped away during past collisions. Others question whether we fully comprehend the nature of dark matter itself. In any case, these unusual galaxies hint that the universe still holds mysteries, and that what we assume to be universal may not be universal after all. The sun resonates like a vast, powerful bell. Deep within the sun, sound waves travel through the plasma, bouncing between layers and setting the entire star into subtle, ongoing vibration. These waves are not like sounds we hear with our ears. They are pressure waves, slow, low-frequency oscillations far beyond human hearing. With highly sensitive instruments, however, scientists can detect them and use them to investigate the sun's inner structure. This field of study is known as helioseismology. By studying how the sun resonates, scientists can chart what occurs deep beneath its surface, its density, rotation, and even its concealed currents of hot gas. In this way, the sun behaves like a musical instrument, immense, intricate, and constantly performing. We simply require the proper tools to listen, and what we detect helps us understand not only our own star, but stars throughout the universe. Galaxies trace filaments composed of something we cannot see. The largest structures in the universe are not made of stars or gas. They are shaped by an invisible substance, dark matter. Over billions of years, this dark matter assembled vast filaments stretching across space. Galaxies tend to form and travel along these strands like beads threaded on a string. We cannot observe the filaments directly, but we infer their presence by watching how galaxies cluster and how light curves as it moves through these regions. The filaments can extend hundreds of millions of light years and link enormous clusters of galaxies. Between them lie immense voids, nearly empty expanses where very little matter exists. These dark matter strands function as a hidden framework for the visible universe, guiding how galaxies develop and where they migrate. And still, we do not know what dark matter truly is. The structure exists, vast, invisible, and quietly binding the cosmos together. Space itself can expand faster than the speed of light. Under normal conditions, nothing can travel faster than light. But space is not restricted by that limit. In the earliest moments following the Big Bang, space expanded so swiftly that regions of the universe were separated faster than light could move between them. This was not motion through space, but the expansion of space itself. Even now, distant galaxies are not speeding away because they are moving rapidly through space. They are receding because the space between us and them is stretching. And if they are distant enough, that expansion causes them to move away faster than light, which is why we will never observe them again. This is not a violation of physics, but a quiet outcome of how space behaves on cosmic scales. The universe does not need to hurry. It simply grows steadily and persistently beyond what we can follow. Our solar system travels through space in a helical spiral. It's easy to imagine the planets circling the sun in tidy, flat loops. But when you zoom out, something more unusual appears. The sun itself is in motion, orbiting the center of the Milky Way at nearly 1,000,000 kilometers per hour. As it moves forward, the planets follow along, not merely revolving around the sun, but spiraling through space behind it. The combined movement forms a helical shape, like a corkscrew or a twisting ribbon. Everything is moving. The planets, the sun, the stars, the galaxy itself. There is no stillness in space, only elegant, continuous drift. Even as we sleep, we trace slow spirals through a galaxy in motion, wrapped in layers of orbits within orbits, a dance so immense that we never feel it. Even emptiness has a temperature. If you travel far enough away from stars, planets, and galaxies into deep intergalactic space, you would find yourself surrounded by what seems like complete emptiness. Yet even the vacuum possesses a temperature. That temperature is around 2.7 Kelvin, only a few degrees above absolute zero. It comes from the cosmic microwave background, the leftover glow of the Big Bang, now stretched and cooled by billions of years of expansion. This faint radiation fills the entire universe. No matter where you go, it is present. It is the quiet thermal imprint of the early cosmos, still lingering, still measurable. And in the distant future, it will cool even more. In a few trillion years, the universe may come close to absolute zero, but never fully reach it. Because even in the deepest emptiness, a trace of heat endures. Quantum fluctuations may have shaped the entire cosmos. At the smallest scales of reality, far smaller than atoms, the universe behaves in unpredictable ways. Tiny random fluctuations in energy can appear and disappear in an instant due to the uncertainty built into quantum physics. According to many cosmologists, those brief random flickers may have been amplified during the universe's earliest moments through a process known as inflation. As space expanded at unimaginable speed, those tiny fluctuations were stretched to cosmic size. They became the seeds of structure, the regions where matter would gather, where galaxies would form, where stars would eventually ignite. In other words, the vast architecture of the cosmos, the galaxies, the filaments, the voids, may all trace back to fleeting random events at the smallest possible scale. Everything we see today emerged from the trembling of nothing. Dying stars can throb like heartbeats over millions of years. Not every star ends its life in an explosion. Some fade more gradually, and in their final phases they can pulse, expanding and contracting in rhythmic cycles. These stars, known as variable stars, shift in brightness over time. In certain cases, the changes are steady and predictable, repeating like a slow heartbeat. The pulses are driven by transformations in the star's outer layers, gases expanding and cooling, then contracting and heating once more. Some stars complete a cycle in just a few days. Others take months or even years. These rhythmic stars have long been used to measure distances in space because their pulsation patterns correspond to their true brightness. They also stand as quiet reminders that even near the end, stars can keep time, not with a clock, but with a long, measured breath. Across cosmic timescales, Earth exists inside a vast bubble of hot gas. If you could observe in wavelengths beyond what your eyes can detect, you would discover that our solar system resides within a large glowing cavity of heated gas. It is called the local bubble, and it stretches hundreds of light years in every direction. This bubble is believed to have been carved out by ancient supernovae, exploding stars that sent shock waves through surrounding gas, heating it and sweeping it aside. Now, our solar system drifts quietly through this low-density region, encircled by a shell of warmer gas and dust. It is not dangerous. It is not something we can sense, but it is there, a silent chamber around us, born from violence long ago, now part of the gentle background of our galactic neighborhood. There is a vast empty expanse behind the Great Attractor. The Great Attractor is a mysterious gravitational anomaly, a region of space so massive that entire clusters of galaxies, including our own Milky Way, are slowly drifting toward it. Yet beyond this immense concentration of matter lies something even more unusual, a region known as the dipole repeller, where space appears strikingly empty. It is not merely an area with fewer galaxies. It is a gigantic cosmic void stretching across hundreds of millions of light years. Strangely, its emptiness seems to push galaxies away. Together, the Great Attractor and the dipole repeller create a subtle gravitational tug-of-war that helps shape the motion of our local universe. We are pulled forward by unseen mass and pushed back by the emptiness beyond. It is a reminder that in the cosmos, both presence and absence can guide the paths we follow. Neutrinos pass silently through the Earth and through you. At this very moment, trillions of particles known as neutrinos are moving through your body, and you will never notice them. Neutrinos are extremely light, electrically neutral particles produced in vast numbers by the sun, exploding stars, and even the early universe itself. They interact so weakly with ordinary matter that they can pass straight through an entire planet or your whole body without leaving any trace. A small fraction pass through detectors buried deep underground where rare interactions allow scientists to study them, but most simply continue on their way, unnoticed. These particles are everywhere at all times, quietly streaming through space and matter alike. They travel at nearly the speed of light, and yet they almost never collide with anything. The universe is full of movement, even when everything seems still. The most massive stars can collapse directly into black holes without an explosion. We often imagine the death of a massive star as a dramatic supernova, a brilliant outburst lighting up its galaxy. But for the heaviest stars, the ending can be unexpectedly silent. Some stars are so massive that when they exhaust their fuel, their cores collapse inward and gravity tightens so completely, so abruptly, that even the outer layers fall straight in. No explosion, no luminous farewell, just a sudden disappearance. This phenomenon is known as direct collapse. In an instant, a star disappears, replaced by a black hole, silent, unseen, and overwhelmingly dense. Astronomers have even recorded stars that appeared to vanish without a trace, as though their light simply blinked out. It's a reminder that not every cosmic ending arrives with fireworks. Some fade as whispers into the darkness. Galaxies can circle one another like moons around planets. We often picture galaxies as isolated islands in space, yet many exist in small groups where they interact and even orbit each other. Our own Milky Way, for instance, has dozens of smaller satellite galaxies. The Large and Small Magellanic Clouds are the most well-known. These companions revolve around the Milky Way, like moons around a planet, slowly tracing long elliptical paths through space. At times, larger galaxies draw stars from their companions, creating streams and tidal tails that stretch across millions of light years. Over time, a smaller galaxy may be entirely absorbed. These cosmic dances unfold over billions of years, slow, elegant interactions on a scale almost impossible to imagine. In the quiet depths of space, even galaxies can keep each other company. The brightest explosions in the universe may come from collapsing magnetic stars. There exists a rare type of explosion called a magnetohypernova, and it may rank among the most luminous events the cosmos can produce. A magnetar is a neutron star with a magnetic field trillions of times stronger than Earth's. If a massive star collapses into a magnetar and releases its energy rapidly, it can generate a burst of light and power far exceeding a typical supernova. These events may account for certain long-duration gamma-ray bursts, flashes of high-energy radiation that travel across the universe and briefly outshine entire galaxies. The explosion lasts only seconds, yet its light can reach us from billions of light years away. It is one of the most extreme phenomena in existence, created by a small, dense object wrapped in magnetic fury collapsing inward on itself. The boundary of the observable universe is not the boundary of the universe itself. When we gaze into space, there is a limit to how far we are able to see, roughly 46 billion light-years in every direction. That marks the edge of the observable universe. It is not a wall or a physical barrier, but simply the greatest distance light has had time to reach us since the Big Bang, taking into account the expansion of space. Beyond that horizon, the universe most likely continues. We just cannot observe it yet. And because space is expanding at an accelerating rate, certain regions are receding from us faster than light. This means their light will never reach us, not even given infinite time. The observable universe is like a bubble of sight. not the full extent of reality, but only the portion accessible to us. Beyond it, more galaxies, more stars, perhaps endlessly. Some galaxies launch jets of plasma that extend for millions of light years. At the core of many galaxies lies a supermassive black hole. Sometimes, as matter spirals toward it, not all of that material disappears. Part of it becomes trapped in magnetic fields and is hurled outward in narrow, powerful jets, streams of plasma traveling near the speed of light. These jets can stretch far beyond the galaxy that hosts them, reaching distances of millions of light years. We detect them glowing in radio wavelengths, forming enormous lobes that reveal their reach. Galaxies of this type are known as radio galaxies, and their jets rank among the largest structures in the universe. It is a strange irony that some of the most powerful outflows originate from regions around black holes, where light itself struggles to escape. Even silence, it seems, can leave an imprint. There is a star that orbits the Milky Way in reverse. Most stars within the Milky Way move in the same general direction, following the galaxy's rotation, but not all. At least one known star, named H04375-439, travels the opposite way. Its orbit is retrograde, moving against the flow like a salmon swimming upstream. How did it end up this way? One possibility is that it once belonged to a smaller galaxy that merged with the Milky Way long ago, and its orbit preserves the memory of that earlier system. Another idea is that it was flung into its present path by a gravitational slingshot, perhaps involving a black hole or a dense star cluster. Whatever the cause, it stands as a quiet reminder that not all stars follow the expected pattern. Even within the vast machinery of the galaxy, there are wanderers charting their own course. The center of the galaxy carries the scent of raspberries and rum. It sounds like a joke, but it is true. Astronomers examining the chemical makeup of a dust cloud near the Milky Way's core identified a molecule known as ethyl formator. On Earth, this compound is linked to the flavor of raspberries and the aroma of rum. Of course, the galactic center does not actually smell. The vacuum of space cannot transmit scent the way air can. Still, the presence of such molecules suggests that complex organic chemistry is unfolding in deep space. Interstellar clouds contain alcohols, sugars, and even precursors to amino acids. It is not life, but it is the type of chemistry life could require. So while space may not literally smell like fruit and liquor, it does contain the building blocks drifting silently between the stars. One galaxy is heading directly toward the Milky Way, and they are already beginning to touch. The Andromeda Galaxy is our nearest large galactic neighbor, and it is on a slow collision course with the Milky Way. At present, it lies about 2.5 million light years away, but that distance is shrinking. In roughly 4 billion years, the two galaxies will start to merge. Interestingly, the outer halos of both systems, their immense clouds of hot gas and dark matter, are already overlapping. In that sense, contact has already begun. The eventual merger will resemble a graceful blending rather than a violent crash. Most stars will pass one another without direct collisions. Over time, the two spiral galaxies will combine into a single, larger, elliptical galaxy. We sometimes refer to this future system as Milka. It is a long wait, but the process is already underway. A cosmic encounter unfolding across billions of years. The cosmic microwave background continues to glow all around you. Every region of the universe including the space surrounding you at this moment, is filled with a faint radiation known as the cosmic microwave background. It is the afterglow of the Big Bang, light released when the universe was about 380,000 years old. At that time, the cosmos was a hot, dense plasma. Once it cooled enough for atoms to form, light was finally able to travel freely. That light has been journeying ever since, stretched into microwave wavelengths by the expansion of space. Today, we detect it as an almost uniform glow in every direction. It is not something you can see or feel, but sensitive instruments register it as a kind of cosmic whisper. This radiation is the oldest light we can observe, a quiet signal from the universe's infancy, still echoing through space and time. Some supernovae are driven by invisible collapse rather than brilliant light. Supernovae are famous for their luminosity, colossal explosions that can briefly outshine entire galaxies. Yet not every supernova shines brightly. Some are what astronomers describe as failed supernovae. In these situations, the core of a massive star collapses and forms a black hole, but the outer layers do not erupt outward in a visible flash. Instead, they may fall inward, feeding the black hole in silence. On rare occasions, astronomers have observed stars that appeared stable suddenly disappear from view. No explosion, no fading glow, just darkness. These vanishings suggest a collapse so complete that nearly all the energy is swallowed. The violence is still immense, but most of it remains concealed. It is a reminder that not every cosmic death announces itself. Some unfold in silence. Deep within gravity's influence, there are entire galaxies composed mostly of gas and dark matter. We often imagine galaxies as bright spirals or glowing elliptical systems filled with billions of stars. Yet some galaxies are barely visible at all. These faint systems contain very few stars, but they still possess mass, primarily in the form of gas and dark matter. They are difficult to detect with conventional telescopes and often appear only as dim smudges or through indirect measurements. Some of these galaxies may be failed systems, structures that never formed many stars, perhaps because their gas was stripped away or heated too early in cosmic history. Others might represent temporary stages in galactic evolution. What they share is subtlety. No fireworks, no sweeping spiral arms, just quiet gravitational presence. They remind us that not every galaxy shines. Some simply exist. Black holes can collide and merge in vast cosmic dances. When two black holes orbit each other, they generate ripples in space-time known as gravitational waves. As energy radiates away, the black holes spiral closer together until they unite in a final dramatic instant, two invisible giants becoming one. These collisions do not produce light, but they release bursts of gravitational waves that we can now detect here on Earth. The first such signal was observed in 2015, confirming a century-old prediction by Einstein. Since then, dozens more have been recorded. Each detection tells a story of massive objects colliding in distant galaxies long ago. These mergers occur quietly and invisibly, yet with extraordinary power, converting entire solar masses of energy into waves that ripple across the universe. For a brief moment, the fabric of space itself seems to sing. Some stars fade in slow motion, taking billions of years to disappear. Not every star concludes its life in a sudden explosion. Smaller stars, like our Sun, end much more gradually. After exhausting their hydrogen fuel, they expand into red giants and shed their outer layers into space. What remains is a dense, hot core, a white dwarf. This remnant no longer generates energy. It simply radiates away its residual heat extremely slowly. A white dwarf may require billions of years to cool, steadily dimming until it becomes invisible. A black dwarf. However, the universe is not yet old enough for that to have occurred. Every white dwarf that has ever formed is still glowing somewhere, quietly fading in the darkness. The death of these stars resembles not a firework, but an ember slowly cooling across cosmic time. Time moves more slowly near a black hole than on Earth. In Einstein's theory of general relativity, gravity does more than pull on matter. It bends space and time. The stronger the gravitational field, the more slowly time flows, compared to regions where gravity is weaker. Near a black hole, where gravity is extreme, this effect becomes profound. If you were to orbit just outside the event horizon, time for you would pass far more slowly than for someone distant from the black hole. Minutes near it could equal years elsewhere. This is not science fiction. It is a measurable phenomenon known as gravitational time dilation. We have already observed it in milder form with GPS satellites. Around black holes, it becomes dramatic. They do not merely trap light, they stretch time itself. The void between galaxies is colder than any laboratory on Earth. Far from stars, planets, or even gas clouds, the immense expanses between galaxies are astonishingly cold. Temperatures there fall to just a few degrees above absolute zero, about 2.7 Kelvin. That is colder than any natural environment on Earth, and colder than most conditions we can create even in advanced laboratories. This chill results from the near total absence of particles and energy. There is almost nothing to retain heat, only a sparse scattering of stray atoms, and the faint microwave glow left over from the early universe. These intergalactic voids are the quietest and most solitary places we know, vast and hollow, stretching across millions of light years. They are the universe's deepest shadows, containing only the faint background murmur of creation. The universe is becoming more transparent as it ages. In its earliest era, light could not travel freely. The cosmos was filled with hot plasma, a haze of free electrons and atomic nuclei that constantly scattered photons. But as the universe expanded and cooled, it reached a stage where electrons joined with nuclei to form neutral atoms. Suddenly, light was able to move without obstruction. This event, known as recombination, occurred about 380,000 years after the Big Bang and released the cosmic microwave background that we still observe today. Since then, the universe has grown increasingly transparent. The birth of galaxies and stars introduced new regions of light, and as matter spreads out, there is less and less to block a photon's path. Over time, darkness itself has become clearer. Space, once radiant and opaque, now allows light to pass almost unhindered. We have captured the shadow of a black hole. In 2019, the Event Horizon Telescope revealed the first direct image of a black hole, or more precisely, its shadow. The black hole cannot be seen directly, but the glowing ring of heated gas orbiting it makes its presence visible. This particular black hole resides at the center of the galaxy M87, roughly 53 million light-years away. The image displays a dark circular silhouette, the region from which no light escapes, encircled by a halo of radiation distorted by gravity. Achieving this image required years of global cooperation, synchronizing telescopes around the world to function as a single Earth-sized lens. The outcome was more than a photograph. It was a quiet, scientific triumph, granting us our first real glimpse of one of the universe's most mysterious entities, not through imagination or theory, but through light itself. You can see a galaxy with your own eyes from your backyard. Most galaxies are so distant that even powerful telescopes reveal only faint smears of light. Yet there is one you can observe without any equipment at all, the Andromeda Galaxy. On clear, dark nights in the northern hemisphere, it appears as a soft, hazy oval in the sky, barely visible to the naked eye. It lies more than 2.5 million light-years away, meaning the light reaching you began its journey long before humans existed. Andromeda contains about 1 trillion stars, more than twice as many as the Milky Way, and it is gradually moving toward us. It is astonishing to realize that you can look upward and see an entire galaxy without a telescope, without filters, just the sky, your eyes, and the gentle glow of something vast and ancient drifting through the darkness. A small detector captured the faint whisper of a distant black hole merger. In 2015, an observatory called LIGO recorded something extraordinary, a subtle ripple in space-time originating more than 1 billion light-years away. It was produced by 2 black holes colliding and sending gravitational waves across the universe. These waves are incredibly delicate. By the time they reach Earth, they stretch and compress space by less than the width of a proton. Yet with exquisitely sensitive instruments, we are able to detect them. LIGO and its partner observatories function like cosmic ears, listening for the deepest vibrations of the universe. The discovery confirmed a prediction Einstein had made a century earlier, that even in the silence of space, massive events can generate waves. We can register a single faint chirp from the merger of invisible giants, captured by a small detector on a quiet corner of a small blue planet. Some regions of the universe are receding from us forever. The universe is expanding, and that expansion is accelerating as space stretches ever more rapidly. Certain galaxies are being driven away so quickly that their light will never reach us. Even if we waited indefinitely, the space between us and them would expand too fast for their light to bridge the distance. They have already crossed a point of no return, slipping beyond the cosmic event horizon. Over time, more and more of the universe will fade from sight, not because it disappears, but because its light can no longer reach us. This is not something we will notice day to day, but across billions of years, it means the visible universe will contract. The cosmos is not only expanding, it is also quietly releasing what lies beyond our reach. Some black holes may be primordial, born before any stars existed. Most black holes arise from the collapse of massive stars. But another possibility remains. Black holes formed in the earliest instance of the universe, before stars had even appeared. These are called primordial black holes. They may have originated from tiny fluctuations in the dense, hot conditions shortly after the Big Bang, regions where gravity compressed matter into extremely compact knots. Some of these black holes could be incredibly small, while others might have grown over time. We have never directly detected one, yet if they do exist, they could help explain dark matter, trigger the formation of galaxies, or reveal new insights into the universe's earliest phases. They would be older than stars, older than galaxies, silent relics from the first seconds after time began. Entangled particles may connect distant corners of the cosmos. Quantum entanglement is among the most puzzling phenomena in physics. When two particles become entangled, their properties remain linked no matter how far apart they are separated. Alter one, and the other responds instantly, even across immense distances. It does not transmit information faster than light, but it suggests that reality at the quantum level is profoundly interconnected. Some physicists propose that entanglement could even contribute to the structure of space-time itself, perhaps helping to hold space together. In theory, particles created in the early universe could remain entangled today, stretched across the expanding cosmos. If so, subtle, invisible threads may still connect distant regions. Quantum echoes from the dawn of time lingering in the emptiness between galaxies. The vacuum of space possesses quantum pressure. Even in a perfect vacuum, where there are no atoms, no particles, no radiation, energy still exists. Quantum physics shows that empty space is not truly empty. Instead, it is filled with tiny, restless fluctuations, particles and antiparticles appearing and vanishing, fields shifting subtly, always in motion. This activity generates a pressure known as vacuum energy. On vast scales, this pressure may help account for dark energy, the force driving the universe's accelerating expansion. Unlike other forms of energy, vacuum energy does not thin out as space grows. It remains constant, causing space to stretch faster the more of it there is. It is a strange idea that the more nothing you have, the more something it becomes. The quiet force of emptiness itself may be what is pulling the cosmos apart. Black holes emit faint heat over unimaginable spans of time. Black holes are famously dark, so dense that nothing, not even light, can escape their gravitational pull. Yet thanks to physicist Stephen Hawking, we know they are not entirely silent. According to quantum theory, black holes can release a subtle glow called Hawking radiation. This occurs at the edge of the event horizon, where virtual particle pairs occasionally result in one particle escaping, while the other falls inward. The escaping particle becomes real, carrying away a minute amount of energy from the black hole. Over extraordinarily long periods, this gradual leakage can cause a black hole to shrink and eventually evaporate completely. For a black hole with the mass of the Sun, that process would require more than a trillion years. It is the quietest kind of ending, not an explosion, but a slow and patient fading into nothing. The universe contains more plasma than solid matter. When we think about matter, we usually imagine solids, liquids, and gases. Yet the most widespread state of matter in the cosmos is something entirely different: plasma. Plasma is an ionized gas, a cloud of particles in which electrons and nuclei move freely. It exists inside stars, within the solar wind, throughout interstellar space, and even across the vast regions between galaxies. Most of the visible matter in the universe is in this form. Plasma behaves differently from other states of matter. It responds to magnetic fields, flows like a fluid, and can carry electrical currents over enormous distances. On Earth, we rarely encounter it, except in lightning, flames, or neon lights. But in space, plasma is everywhere, glowing, flowing, and shaping much of what we observe. Gravitational waves travel at the speed of light. Gravity does not merely pull, it can ripple. When massive objects such as black holes or neutron stars collide, they generate waves in the fabric of space-time itself. These gravitational waves stretch and compress space as they move outward in all directions, and they propagate at the speed of light, the fastest speed possible in the universe. It took decades to build instruments sensitive enough to detect them. Now we can listen to these cosmic ripples from Earth. Each wave carries information about distant cataclysms, how much mass was involved, how rapidly the object spun, even how severely space was distorted. Gravitational waves are silent to human ears, yet they are real, measurable, and surprisingly subtle. Tiny shudders within the deep structure of the cosmos. The cosmic web links galaxies across the universe. If you could chart the positions of galaxies on the largest imaginable scale, you would uncover something remarkable. A vast interconnected pattern of filaments and voids known as the cosmic web. Galaxies do not sit alone in space. They gather along invisible threads of dark matter and gas that stretch like tendrils between clusters. Where these filaments intersect, we find superclusters, immense knots of galaxies. Between them lie enormous quiet voids that are nearly empty. The cosmic web is not something we can see all at once with a telescope, yet its structure emerges from large sky surveys. It resembles a network of foam, even the branching patterns of neurons. It is the shape of the universe on its grandest scales, not random, but woven, as if grown rather than assembled. The James Webb Telescope can observe galaxies that no longer exist in the form we see. The James Webb Space Telescope was designed to look farther than ever before, and in doing so, it also looks further back in time. Because light requires time to travel, distant galaxies appear to us as they were billions of years ago. Some of the galaxies Webb observes may no longer exist in the way we see them. They may have merged, dimmed, or transformed completely, but their light is still arriving, a snapshot fixed in time, continuing to cross space long after its source has changed. This is one of the quiet peculiarities of astronomy. Telescopes do not show us what exists right now. They reveal what was present at different moments throughout the universe's history. Every deep field image is also a kind of time machine, a gallery of vanished light. Distant galaxies shine with light that left them before Earth even formed. When you look at a galaxy several billion light-years away, you are not just seeing distance, you are seeing age. The light from that galaxy began traveling long before Earth existed, before the sun ignited, before our solar system had begun to take shape. Some galaxies we observe today emitted their light over 10 billion years ago. That glow traveled through expanding space, stretched and reddened along the way, until it finally reached our telescopes. In a sense, we are watching the universe's ancient past unfold in real time. The stars visible in those galaxies may already be gone, yet their light remains. A gentle reminder that the night sky holds stories older than Earth itself. Entire galaxies can disappear behind clouds of dust. Even something as immense as a galaxy can be concealed by dust. In certain areas of space, thick clouds of interstellar dust block the light behind them. This dust is not like what gathers on a shelf. It consists of tiny grains of carbon and silicates drifting within cold, molecular clouds. When a galaxy lies behind such a cloud, much of its visible light can be obscured. We detect it only by observing in infrared, radio, or X-ray wavelengths, which pass through dust more easily. Astronomers have uncovered entire galaxies this way, hidden behind what once appeared to be empty sky. Even in space, appearances can mislead. Darkness does not always signify absence. Sometimes it simply means waiting to be revealed in the proper light. Some galaxies are encircled by perfect rings of lensed light. At times, the gravity of a galaxy bends the light coming from something even farther away. If the alignment is precise, this bending produces a phenomenon known as an Einstein ring, a flawless circle of distorted light. It is a type of gravitational lensing in which the mass of the foreground galaxy curves space-time, acting like a lens for the background light. Einstein rings are rare yet striking, luminous loops suspended in space, created not by motion but by alignment and gravity. The light may originate from a distant galaxy, a quasar, or even a supernova. These rings allow astronomers to measure galactic mass, map dark matter, and study the early universe. They are silent, perfect illusions, natural lenses shaped by the geometry of space itself. The universe may be infinite. When we look up at the stars, it is natural to wonder whether there is a boundary somewhere, an edge to everything. Yet current observations suggest that space might extend without limit. We can observe only a finite region, the observable universe. Beyond that horizon, the universe may continue endlessly. No boundary, no central point, just more galaxies, more stars, more space. If that is the case, then most of the universe will always remain beyond our reach. No matter how far we look or how long we wait, we will never see it all. An infinite universe does not imply infinite possibilities, but it does suggest endlessness, a quiet vastness that stretches on gently without conclusion. Cosmic rays strike Earth from deep space. Every second, high-energy particles known as cosmic rays collide with our planet. Some originate from the Sun, others from distant regions of the galaxy, or even beyond. They consist of protons, atomic nuclei, and other fragments accelerated to extraordinary speeds by exploding stars, black holes, or unknown cosmic forces. Most are deflected by Earth's magnetic field or absorbed by the atmosphere, but some reach the surface, and a few even pass through you. These particles are largely harmless in small amounts, yet they serve as a constant reminder that space is not empty. It is filled with motion, energy, and invisible messengers from distant events. From time to time, a cosmic ray strikes a detector and tells a story that began light years away. The journey of a particle from a supernova to your sky. There may be no such thing as before the Big Bang. The phrase before the Big Bang feels natural, yet it may not actually make sense. According to general relativity and many cosmological models, time itself began with the Big Bang. That event was not only the birth of matter and energy, it was also the beginning of space and time as we understand them. Asking what came before is like asking what lies north of the North Pole. Some theories propose an earlier state or a previous universe, while others describe a quantum realm where time behaves differently or may not exist at all. But in most models, before the Big Bang is not a place we can meaningfully explore, even in thought. The Big Bang was not an explosion within space. It was the origin of space itself. Astronomers once mistook quasars for nearby stars. When quasars were first discovered, they appeared as faint, point-like objects, almost identical to ordinary stars. Yet their light behaved strangely. Their spectra were unusual, and their brightness changed in puzzling ways. It took years to realize these were not stars at all, but extremely distant galaxies with highly active centers. A quasar is powered by a supermassive black hole surrounded by a swirling disk of hot infalling gas. That gas heats up and radiates with astonishing intensity, sometimes shining brighter than the rest of the galaxy combined. The earliest quasars observed were so distant that their light had traveled billions of years to reach us, and still they looked like tiny stars. A case of mistaken identity that turned into one of the brightest discoveries in astronomy. Our local group of galaxies is moving toward a hidden region. The Milky Way does not remain still. Together with the Andromeda Galaxy and dozens of smaller companions, it drifts through space as part of a loose collection called the Local Group. And this group, in turn, is traveling towards something even larger, a gravitational anomaly known as the Great Attractor. Beyond that lies an even more mysterious region, the Shapley supercluster, and perhaps others concealed by the dense plane of our own galaxy. These distant concentrations of mass exert a pull we can measure, even though we cannot yet see all of them. It is as if our entire galactic neighborhood is sliding towards something immense, shrouded in shadow. We do not know exactly what lies in that direction, only that we are gradually moving toward it, drawn by the weight of unseen giants. We are living in the universe's stellar springtime. At this moment, the cosmos is filled with stars, burning, forming, exploding. Yet this abundance is a relatively recent chapter. For the first few 100 million years after the Big Bang, there were no stars at all. The first ones ignited in darkness, illuminated their surroundings, and began the long process of cosmic evolution. Since then, star formation has risen, reached a peak, and gradually declined. We now exist in what might be called a cosmic spring, a period when new stars still form, though fewer than before, and far more than will form in the distant future. One day, the last stars will be born. After that, the universe will slowly dim. But for now, it remains lit with new beginnings, bright enough for wonder, quiet enough for rest. In the distant future, stars will cease to form. Star formation depends on cold gas, clouds of hydrogen and helium collapsing under gravity. Over time, that fuel becomes scarce. It becomes locked inside stars, expelled by supernovae, or heated beyond usefulness. Billions of years from now, galaxies will exhaust the material needed to create new stars. The ones that remain will age, burn out, and fade away. First, the blue giants, then stars like our sun, then the red dwarfs, until even the slowest burning embers cool into darkness. The universe will not end suddenly. It will dim gradually, quietly, gently. What remains will be black holes, white dwarfs, neutron stars, and the silence of a cosmos grown cold. Not tragic, simply still. Most matter in the universe is invisible. When we observe stars, galaxies, and nebulae, we are seeing only a small fraction of what truly exists. Most of the matter in the cosmos does not shine. It neither emits nor reflects light. This unseen substance is called dark matter. Although it has never been directly detected, we know it exists because of its gravitational influence. Galaxies rotate faster than visible matter alone can explain. Light from distant objects bends more than expected. Galaxy clusters remain bound with greater strength than their luminous mass allows. All of this points to hidden mass, more than 5 times the amount of ordinary matter. Dark matter is everywhere, shaping the universe's structure. We simply cannot see it. It is a silent, invisible framework holding everything else in place. Light from the earliest galaxies has been stretched by cosmic expansion. As light travels through space, it does not merely move, it stretches. This happens because the universe itself is expanding. As space grows, it pulls light waves with it. The light that left the first galaxies billions of years ago has been stretched into longer wavelengths, shifting from visible light into the infrared. This process is known as redshift, and it is one of the primary tools astronomers use to measure distance and time across the universe. The more stretched the light, the farther and older its source. With telescopes like James Webb, we can now observe that ancient light softened and reddened by its journey. What began as the glow of young stars now arrives as a faint whisper, extended by the expansion of space itself. The universe may be a hologram. It sounds like science fiction, yet some physicists have seriously considered the possibility that our three-dimensional universe might be a projection from a deeper, two-dimensional reality. This idea is called the holographic principle. It emerged from research on black holes, where information about everything that falls inside appears to be encoded on the surface, rather than within the volume of the black hole itself. Some theories propose that the entire universe might function in a similar way. What we experience as depth and space could be a kind of mathematical projection arising from information written on a distant boundary. It is not proven and likely has no impact on daily life, but it offers a gentle reminder that reality, even when it feels solid, may not be exactly what it seems. Space itself may be granular at the smallest scale. To the unaided eye, space appears smooth. Even under magnification, it seems empty and continuous. Yet certain theories of quantum gravity suggest that space may consist of tiny discrete units like grains or pixels in a digital image. This smallest possible scale is known as the Planck length, about 10 to the minus 35 meters. At that scale, apparent smoothness may dissolve into something more fundamental, a grainy, foamy texture of space-time itself. We do not yet possess the tools to observe or test this directly. But if it is true, then everything, stars, galaxies, thoughts, even sleep, unfolds not within a perfect void, but inside a universe structured all the way down. There are stars that spin faster than kitchen blenders. Some stars rotate so rapidly that their equators bulge outward and their surfaces blur into streaks of motion. Neutron stars, the dense remnants of massive stars, go even further. A subtype called a millisecond pulsar can spin hundreds of times each second. That means an entire star, a sphere of nuclear matter the size of a city, rotates faster than a blender blade. These objects emit beams of radiation that sweep through space like cosmic lighthouses, ticking with extraordinary precision. Many are locked in tight orbits with companion stars, pulling in matter and gaining speed. They are among the fastest rotators known and also some of the most accurate clocks, ticking silently in the night. The universe may conclude in a slow and silent fading. Cosmologists once speculated that the universe might eventually collapse back in on itself. But current evidence points toward a different destiny, gradual, unending expansion. As galaxies drift farther apart and the birth of new stars declines, the night sky will grow darker. Existing stars will burn out one after another. Black holes will evaporate. Matter itself may eventually decay. The universe will become colder, quieter, and more empty, a condition known as heat death. It is not a sudden catastrophe, but a prolonged and gentle dimming. Over trillions of years, the cosmos will settle into stillness as energy thins out and structures dissolve. Not an ending of fire or ice, but of silence, a universe that whispered itself into existence and may one day whisper itself away. Some galaxies generate super winds that blow material into space. In certain galaxies, particularly those with active black holes or intense star formation, powerful winds can surge outward from the center, carrying gas, dust, and even young stars with them. These galactic superwinds can extend tens of thousands of light years, pushing matter into intergalactic space. They are driven by radiation, magnetic forces, and the explosive power of supernovae. Over time, these winds can strip a galaxy of the gas needed to form new stars, leaving it quiet and red. At the same time, they disperse heavy elements into the cosmic web, seeding future generations of stars and planets. In this way, a galaxy breathes, drawing in matter, igniting life, then exhaling into the void. The far future of the cosmos resembles an endless, dark ocean. Trillions of years from now, the universe will appear vastly different. Galaxies will have drifted so far apart that each will seem isolated in darkness. New stars will no longer form. Old stars will burn out. Even the faint glow of white dwarfs will fade. What remains will be cold remnants, black holes, and the faint echo of ancient light. Over unimaginable timescales, black holes will evaporate, and even matter itself may decay. Eventually, only scattered particles will drift through empty space, silent, slow, alone. This future is known as the heat death of the universe. Yet it is not a sudden end. It is a vast stillness, a cosmic ocean without waves, wind, or shore. We might be living inside a vast cosmic void. The universe contains clusters of galaxies, and between them lie enormous empty regions known as voids. These voids stretch across hundreds of millions of light years and hold very little matter. Some researchers suggest that we may currently reside within one of these underdense regions, less crowded than the average cosmic environment. If that is true, it could help explain certain observations, such as measurements of the universe's expansion rate or patterns in the cosmic microwave background. Living inside a void would not affect daily life, but it would mean that what feels like emptiness is part of a much larger structure, the quiet interior of a cosmic bubble drifting gently through a web of unseen gravity. Magnetars possess magnetic fields trillions of times stronger than Earth's. A magnetar is a type of neutron star, a city-sized remnant of a collapsed massive star, with an extraordinarily powerful magnetic field. Earth's magnetic field is strong enough to guide a compass. A magnetar's field is so intense that it could erase data from thousands of miles away, distort atomic structures, or tear matter apart. These magnetic fields gradually weaken over time, but while they persist, they generate flares and bursts of high-energy radiation. A single magnetar flare, even from across the galaxy, can be detected on Earth. No laboratory could reproduce such power. They are among the most extreme objects in existence, dense, silent, and wrapped in invisible force, like stars reduced to memory and magnetism. The largest known structure in the universe is a giant quasar group. In 2013, astronomers identified an immense formation composed of quasars, the luminous cores of distant active galaxies. extending more than 4 billion light-years across. This structure, called a large quasar group, is so vast that it challenges our understanding of cosmic uniformity. According to prevailing theory, the universe should appear relatively smooth on the larger scales, without structures exceeding a certain size. Yet this quasar group surpasses that theoretical boundary. It consists of dozens of quasars linked across an enormous region of space, suggesting that the early universe may have developed larger patterns than previously thought. Whether it represents a true physical structure or a statistical coincidence remains debated. Either way, it reminds us that the universe is more intricate and perhaps more interconnected than our models always anticipate. Black holes can twist space into a funnel of time. A black hole does more than trap light. It warps space-time itself. As one approaches the event horizon, space curves inward and time slows. To a distant observer, time near the black hole appears to creep. At the very edge, it nearly halts. This distortion forms something like a funnel in the geometry of space, narrow, steep, and one-way. Inside, every path leads toward the center, the singularity. The closer you draw, the more space and time seem to exchange roles, with inward becoming a direction in time rather than space. There is no return. This twisting of space-time is not merely poetic imagery. It is geometry shaped by gravity, inscribed into the fabric of reality itself. Some regions of the universe may never see each other again because the universe is expanding, and doing so at an accelerating rate. Certain parts are already moving apart faster than light can travel. This means that even if we waited forever, light from those regions would never reach us. The same is true in reverse. There are places we can never send a signal to because the space between is stretching too quickly. Over time, more of the universe will slip beyond reach. Each galaxy will become an island, isolated in darkness. This does not violate the laws of physics. Nothing travels through space faster than light, but space itself can expand steadily and irresistibly, separating one part of the cosmos from another forever. The heaviest element forged in stellar explosions is gold. Gold is rare on Earth, not only in our economy, but in the universe itself. It cannot be created inside the core of an ordinary star. Instead, it forms during the most extreme events, collisions of neutron stars or certain types of supernovae. In those moments, atomic nuclei are crushed together under extraordinary pressure and heat, producing heavy elements such as gold, platinum, and uranium. These newly formed atoms are then scattered into space, mixed into gas clouds, and eventually incorporated into new stars, planets, and even people. Every gold ring, every speck of it, was born in a cosmic catastrophe, a quiet trace of violence now resting in your hand. In that sense, gold is not only beautiful, it is ancient, it is stellar. It comes from a universe that forges treasure in fire. The space between galaxies expands while light travels through it. When we observe light from distant galaxies, we see it as it was long ago, but also stretched by the space it crossed. As the universe expands, the distance light must travel increases. That means the light itself is stretched. Its wavelength lengthens, shifting toward the red. This is known as cosmological redshift. The light is not slowing down or losing energy through collisions. The space it moves through is simply growing. In effect, the universe stretches the signal on its journey to us. When we look at distant galaxies, We are seeing more than age or distance. We are seeing how space has changed since the moment that light began traveling, a silent record of the universe's steady breathing. There are sound waves frozen into the structure of the cosmos. In the early universe, before atoms formed and light could move freely, matter and energy were tightly linked in a hot plasma. Within that plasma, pressure and gravity generated oscillations, ripples of compression and rarefaction, like sound waves traveling through air. These acoustic waves left an imprint on the density of matter, a kind of frozen echo. Today, we observe that imprint in the distribution of galaxies, a preferred separation between galaxy pairs, like a standing wave preserved in space. This phenomenon is called baryon acoustic oscillation. It is subtle, yet measurable, a fossil trace of cosmic sound ringing out from a time before the universe became transparent, a wave that never entirely fades, quietly shaping the structure of everything we see. Galaxies can be consumed by larger ones without leaving a trace. Over the immense timescales of cosmic evolution, galaxies do not simply drift alone. They interact, collide, and sometimes devour one another. When a smaller galaxy ventures too close to a larger one, gravity can tear it apart. Its stars are drawn into long streams, absorbed into the larger galaxy's halo, and eventually blended so completely that the smaller system disappears from sight. Around the Milky Way, we have discovered remnants of such mergers, stellar streams arching across the sky, once belonging to other galaxies. This process is known as galactic cannibalism. Yet it is slow and graceful rather than violent, not sudden, but inevitable. Over time, large galaxies grow in this way, not by building, but by quiet assimilation. One galaxy absorbed into another, leaving only a faint ripple among the stars. There are stars that flicker like fireflies in the night. Not all stars shine steadily. Some pulse, shimmer, dim, and brighten in rhythmic cycles. These variable stars change for many reasons: internal pressure waves, surface eruptions, or eclipsing companions. From Earth, they appear to blink softly in the sky, following a slow stellar rhythm. Some complete their cycle in hours, others take years. These variations are not random. Many are remarkably regular, functioning like celestial clocks. Astronomers use them to measure distances across the universe. A single repeating flicker can reveal how far away a star is and how luminous it truly is. Stars do not merely burn. Some of them breathe. Some black holes wander through space alone. Not all black holes reside at the centers of galaxies. Some roam freely. A black hole can be ejected from its birthplace through gravitational interactions, hurled from a galaxy during a collision, or flung away by the recoil of a merger. Once expelled, it becomes a rogue object, drifting silently through interstellar or even intergalactic space. These wandering black holes are difficult to detect. They emit no light unless they encounter gas or tug on nearby stars. Yet they likely exist, traveling unseen through darkness, unbound. They possess no orbit, no companion, no home, only mass, motion, and the deep gravity of something that collapsed inward and never stopped falling. Even black holes can be kicked across a galaxy. When two black holes merge, the violent event releases a burst of gravitational waves. If those waves are emitted unevenly, the newly formed black hole can receive a recoil, a gravitational kick powerful enough to propel it at thousands of kilometers per second. Some black holes may be launched entirely out of their galaxies. destined to drift alone through intergalactic space. Others settle into wide, wandering paths. These recoiling black holes are difficult to detect, yet astronomers believe they are out there, quiet travelers propelled by the memory of their own collision. Even the heaviest, most firmly anchored objects in the universe can be set in motion by the right kind of wave. Some stars are stripped down to bare carbon cores. When a star like our Sun reaches the end of its life, it sheds its outer layers and leaves behind a core, a white dwarf. Certain white dwarfs consist mostly of carbon, and under the immense pressure of their own gravity, that carbon can crystallize. In other words, some stars become enormous diamonds. These stellar diamonds are roughly the size of Earth, but far more massive, glowing faintly with residual heat. They no longer fuse atoms, yet they continue to shine for billions of years before cooling into darkness. Astronomers have even observed pulsations in some white dwarfs, a kind of ringing like a bell that has been struck. A silent cooling jewel drifting through space. Once a star, now a crystal of ancient fire. Most of the universe's history has yet to unfold. 13.8 billion years may sound immense, but when you imagine the entire future of the universe, not just tomorrow or a million years from now, but trillions of years ahead, we are still near the beginning. Stars are still forming. Galaxies are still assembling. Black holes still glow with the heat of infalling matter. In the distant future, stars will fade. Galaxies will separate. The universe will grow cold and quiet. But that era has not begun. Right now, we live in a moment of light, a brief golden season when the cosmos is alive with motion and change. The past is vast, but the future is vaster still. Supernova remnants continue expanding for thousands of years. When a massive star dies, it erupts in a supernova, a brilliant explosion that can briefly outshine an entire galaxy. Yet the event does not end with the flash. The shockwave expands outward for centuries or even millennia, sweeping up gas, dust, and everything in its path. These expanding shells of debris are called supernova remnants. They glow across many wavelengths: radio, X-ray, visible light, and their shapes reveal the story of the blast. Some form delicate filaments, others turbulent clouds. The Crab Nebula is one such remnant, still spreading outward from an explosion observed on Earth in the year 1054. Supernova remnants are the slow exhalations of dead stars, continuing long after the initial light has faded. Light from a distant star can be bent by a single planet. We usually imagine gravity curving light on immense scales, by stars, black holes, or galaxies. Yet even a planet can do it. If a planet passes directly between a distant star and Earth, it can act as a small gravitational lens, amplifying and slightly distorting the starlight. This effect is known as microlensing. It is subtle and uncommon, but powerful enough to reveal planets we could never observe directly, even in other galaxies. A brief flicker in brightness, a gentle curvature in the light, and suddenly a hidden world is uncovered. The planet itself may be cold, dark, and unseen, but its gravity bends the starlight just enough to announce its presence. The universe once glowed with a deep orange light. In the early period after the Big Bang, the cosmos was a hot, dense plasma radiating intense brightness. As it expanded and cooled, that glow gradually shifted. When the temperature fell to around 3000 Kelvin, the first atoms formed and light was finally able to travel freely. At that moment, the universe would have appeared orange. not the blue-black of today's night sky, but a warm radiance filling all of space. Over time, that light was stretched by cosmic expansion into the faint microwave glow we detect now, the cosmic microwave background. Long ago, however, the entire cosmos shimmered with orange light, as if illuminated from within, a quiet ember slowly fading into time. Some regions of the universe cool more slowly than others. As the cosmos expands, it cools gradually, like an immense oven slowly being turned off. But not every region cools at the same pace. Areas containing more matter or trapped radiation retain heat for longer. Clusters of galaxies, for example, hold hot gas that remains warm for billions of years. Other regions, more isolated, cool more quickly. These temperature differences influence how structures form, how stars evolve, and how long certain processes endure. Even in a universe governed by simple laws, local variations exist. Warmer pockets, slower declines, subtle delays in the great unfolding. The universe does not cool like a machine. It cools more like weather, uneven, textured, and quietly dynamic. We might one day witness the birth of a new universe. Some cosmological theories suggest that new universes could form within our own, budding off through quantum fluctuations, black holes, or mechanisms not yet understood. If such an event occurred, it would likely happen far beyond our ability to observe. Yet in principle, we might detect signs. A rapidly expanding bubble of new physics separating from our familiar reality. We do not know whether this has ever happened. We do not know if it ever will. But the possibility remains that somewhere, someday, the quiet darkness of our universe could give rise to something new, a beginning nested within an ending, a whisper emerging from silence. The cosmos is still resonating from its earliest moments. In the first fraction of a second after the Big Bang, the universe expanded explosively in an event called inflation. That surge left behind ripples, tiny quantum fluctuations stretched across space. These ripples became the seeds of all future structure. Galaxies, stars, planets. They also left echoes. We observe them in the cosmic microwave background as subtle temperature variations, and one day we may detect them as primordial gravitational waves, faint rhythmic pulses in the fabric of space-time itself. The universe may seem calm now, but it still carries the memory of that first vibration, like a bell humming softly long after it was struck. The universe is vast, and you are one way it becomes aware of itself. Of all the quiet wonders in astronomy, perhaps the most astonishing is this: you are made of stardust. The carbon in your body, the calcium in your bones, the iron in your blood, all were forged in stars, scattered through space, and gathered into life. You are not separate from the cosmos. You are a moment of it made conscious, a flicker of awareness in a universe that otherwise only moves, burns, and cools. In that sense, the universe has grown eyes. Through those eyes, it looks back at itself, marvels at itself, dreams of itself. And even now, as you drift towards sleep, it continues dreaming. Thank you for spending this time here, floating through the cosmos with me. We have crossed immense distances, past dying stars and newborn galaxies, listened to ripples in space-time and echoes from the first moments of creation. And somewhere within it all, in the light of ancient stars, in the silence between galaxies, in the soft shimmer of dust, there was you, breathing slowly, thoughts softening, perhaps already asleep. This universe holds motion and mystery, but also stillness. It contains heat, light, and gravity, yet it also contains peace. And the fact that we can know it piece by piece, in calm and quiet, is something truly beautiful. So wherever you are now, fully awake or drifting beyond the edge of thought, may your dreams tonight be gentle. May your body rest like starlight on water. And may you carry with you, even faintly, the memory of a universe that glows not only above you, but within you. If you are still awake, you can continue to the next chapter. And if you would like to drift off to more softly told stories filled with wonder, consider subscribing. There is always more to explore, one sleepy soul at a time. Good night.